you so much for introducing me so nicely.
This meeting is being recorded.
I am happy to be here at the Astrobiology Academy. It's a big honor to me to speak here to such a very big audience. I'm Theresa Lueftinger, working at the ESA European Space Agency, ESA ESTEC, and I'm the Ariel project scientist, so responsible for the science mission management aspects of the Ariel exoplanet space mission, which I'll go into more detail later on. Really happy to be here, and I hope to entertain you a bit within the next half hour to 40 minutes. First part of my talk will be dedicated to the Ariel space mission, and I'll talk a bit later on, I think that has been mentioned already, also on how stars and stellar magnetic field stellar activity influence exoplanets, a very important aspect we need to take into account when doing research on exoplanets and on habitability. But first, before we go into exoplanet science directly, let us maybe take a step a bit back into the bigger structures of the universe. You might wonder why, but as you'll see on the next slide within the next few minutes. Let's have a look at the bigger structures of the universe. So what you're seeing here, what I'm showing you here, it might be familiar to many of you, is actually a simulation of the universe around us that shows big network-like structures with galaxy clusters and filaments along these galaxy clusters. And there is a tiny region to the bottom left that is zoomed in the next rectangle and then zoomed out and out again. So the pink rectangle you see on the bottom left is zoomed out into the bigger one to the top right. And what you see here is the really huge scales we are facing when we're having a look at the universe. So you see that the white bar here is reflecting 500 million light years. So 500 million times the light is passing in the time scale of a year. And then you have 150 million light years when you zoom in again, and there again, 35 million light years on the top left. And what you see there is, again, lots of galaxy clusters with lots of millions of stars. And what we actually know in the meantime, that more or less every one of these stars should roughly have one exoplanet. That's why I'm telling you all that story, to get maybe a bit of an idea with which kind of scales and which kind of hundreds of millions of exoplanets and even more we are dealing here and facing at. So our Milky Way, again, in another picture here, has about 100 million light years of diameter, so 0.1 million light years. If you compare it to the numbers before, you see how big the difference there is, and is containing 100 to 300 billion of stars. And almost all of them have a planet. So we are really facing really huge, unimaginable numbers there, actually. For me, it's not really possible to really face that. But that's what we're actually confronted with. We haven't detected so many of them yet. And actually, the very first detection of an exoplanet was reported. Yes?
Sorry to interrupt you, but the screen seems to be, we don't see it in full screen mode. We see a fraction of it. Maybe okay. we see it in smaller size again.
Did it work before?
I think in the first introductory slide, it looked like okay, but not in this one. Yeah, this is wrong too. But
this is okay or not?
It seems so, but maybe we can get out of the full screen mode, because I don't see if we're missing too much. Mm-hmm. Apologies, everyone. Yeah, it looks like we are missing quite a lot.
Oh, that is strange, because I see it very normal.
Okay, so how about we see it in thumbnail mode? If you put it on the left, I think if you that's correct. So I think that would do the trick. We can better see it this way, if it's okay with you.
Yeah. So if I do that, it's again.
Yeah, it breaks out. The right part and the bottom part are broken apart.
Okay,
sorry.
That's strange. It never happened so far, but you always face new things, right?
Yeah.
Okay. So I'll do as you say. Maybe I increase that window a bit then.
Yeah, now we don't see it again. Now it is. Yeah, that works for us, if it's okay with you.
Yeah, sure, of course.
Thank you. So sorry to interrupt.
Okay, that might be even better. So shall I keep it as is, or and sharing is fine?
Yeah, now it's sharing.
Okay, good. So and I start from where I stopped before. It's okay to continue with slide number 4 now.
Absolutely, yeah. Thank you.
Okay, good. So I've walked you through the big dimensions of our universe and the sheer unimaginable number of exoplanets we are very likely having in the universe as well. And the first one was detected in 1995. So it was the first confirmed detection quite a bit of time ago. And in 2019, as some of you might know, or many of you might be aware of, the Nobel Prize has been dedicated to this detection. So Michel Mayor and Didier Queloz got the Nobel Prize for the detection of the first exoplanet. And currently we are facing a number of 5,363 planets detected and confirmed, where among those 3,960 are in planetary systems. So quite a big number detected already, but we don't have actually a lot of information of those planets. And that's one of the motivations for the Ariel mission. That's a number I checked for you today in the afternoon on a very good website, which is called exoplanets.eu. So if you want to check the current detections and the properties of exoplanets, please just go there and have a look at that page. Having detected this quite big number of exoplanets, actually, we also see that there is a big diversity of exoplanets out there in space. So we face any kind of systems with huge gas giants very close into the star, also further away, and we haven't detected the so-called second solar system yet. So we do not know yet if the solar system is unique or not, if there are many of those. So that's for the future to come, for the more detections in the coming years, to be able to confirm if the solar system is unique, or if we will ever detect the second Earth or not. To face that quest, ESA and also other agencies, other organizations have launched or have developed quite a few exoplanet missions. ESA has really quite a few satellites working for the field. So there was Corot already several years ago. Then Hubble was never really supposed to do analysis of exoplanets, but in the meantime is doing so. The same for Gaia. Then Cheops is up and running. You might have heard of that mission that is defining masses and radii of detected exoplanets. Plato is coming up very soon. So with Plato, we really hope to detect the very first second Earth. It has not been detected yet, as mentioned, but we hope to find a second Earth with the Plato mission, which will be launched in 2026, 2027 officially. JWST is up and running as well, and doing research on exoplanet atmospheres. And then Ariel is coming up, where a big part of my talk will be dedicated on, and my heart is very close to that mission, of course. So Ariel is the so-called atmospheric remote sensing infrared exoplanet large survey mission. But before going into details of Ariel, let me drive you a bit through the different methods we are going to apply with this telescope, and also detection methods for exoplanets, which not everybody of you might have heard of yet. And let me also point out that when having a look or when observing exoplanets, we are facing the very big challenge that we want to observe a comparably tiny dot around a star that is very bright and very shiny, and the planet does not emit any light usually at all. So we really need very, very precise, very, very good instruments to be able to detect these tiny, comparably tiny planets around a bright, shiny star. Several instruments have been developed already, as I've mentioned, also telescopes from the ground to exoplanet observations. And one of the methods that is used is the so-called transit method, where we take advantage of the fact that some of the many, many planets that are likely out there in space, in our line of sight, they transit in front of the star. So when the planet is moving around the star, it's crossing our line of sight. And if our instrumentation is sensitive enough and measuring precisely enough, we see a tiny dip as soon as the planet crosses the star. And that's the so-called primary transit. And again, when the planet is crossing behind the star, we see the secondary transit, so another change in light. And depending on how this so-called light curve looks like, we can also determine how big the planet in relation to the stellar size is, where in front of the star it's transiting, and so on. So we get quite a bit of information out of these transits. Another method that should be mentioned, it's not really applicable to Ariel, but I wanted to mention it for the matter of completeness, is the radial velocity method, a method where many planets have been detected already, based upon which many exoplanets have been detected already as well. And it takes advantage of the fact that a mass, the planet around the star, is causing a tiny wobble comparable to the Doppler effect, more or less, Doppler effect on light in this respect. And if we measure the spectrum of the star, we see the spectral lines moving around a bit. And from this wobble, from this moving, we can determine how massive the planet is. So the more massive, the bigger the planet is, the bigger is this wobble actually. And this is indeed the method where the first transit, where the first exoplanet 51 Pegasi b has been detected in 1995. A method that Ariel is applying at the same time with the transit method. So we are not detecting, but we are monitoring exoplanets very carefully. And we are observing the transit of an exoplanet, as I was showing you before. But what we are doing centrally is applying the so-called transit spectroscopy method, which to me is really, it is still really fascinating that this is working at all. Remember, it's just a tiny black dot in front of a star, and we can even get the spectrum of the atmosphere of such a planet, so we can determine what the atmosphere is composed of by observing its spectrum. So what we take advantage of is there, and in this method, is that when the planet crosses the star, there is always a certain phase where the stellar light is shining through the planetary atmosphere. We again use a spectrograph that is disentangling or measuring the spectrum in a way where different wavelengths, we can detect the different lines that can be attributed to a certain chemical species in the end. And when we measure those lines, we can determine how the chemistry of a planetary atmosphere is, which elements are present in this atmosphere. So in this picture to the lower left, you see the planet is crossing in front of the star, the stellar light is shining through. And if we measure the spectrum with the star and the planet, so when the planet is crossing in front of the star, we get the star plus the planet. Then when the planet has disappeared behind the star, we can measure only the stellar spectrum. And if we deduce those spectra from each other, we get the planetary spectrum. So as I said, still fascinating to me that this is working at all, but it does. And we are benefiting for Ariel from this method. So just to show you how this would look like for planets we know quite well, Venus, Earth, and Mars. So that's how the Earth spectrum would look like. The Venus spectrum here with a lot of CO2 in it, as you all might know. And the Mars spectrum, which doesn't show a lot of features, but it's there as well. And you also see the difference of the spectra, and you might guess, or you maybe directly see already, why the Earth has a livable atmosphere and Venus does not really. So showing you in a video, which might make it even more instructive. You have the planet crossing into the line of sight, crossing in front of the star. Stellar light is shining through. And if you have the according instrumentation in space or on ground, you can detect the spectrum of the planet, where in this case, for the star, for the planet, unexpectedly high amounts of barium have been detected. That was an ESO press release some time ago. So for the Ariel mission, we are doing exactly these things. We are measuring the transit of the star, of the planet in front of the star, and also get the spectra of the planetary atmospheres. And Ariel, just for the basics around it, the cornerstone information, it's the 4th medium class mission within ESA's Cosmic Vision Science program. It was selected in March 2018, then adopted in November 2020 at the SPC in number 165. So that's this science program committee that ESA calls to get missions adopted or not. We want to study the atmospheres of exoplanets. We are aiming for a launch in 2029 on an Ariane 6.2, and planning to go in so-called Lagrangian orbit to Lagrange point 2 with a nominal mission lifetime of 4 years, and then we hope we can get extended for another 2 years. Stakeholders are the European Space Agency, the Ariel Mission Consortium, and NASA is contributing as well with detectors, and possibly also JAXA and CSA are joining. So the main scientific questions we want to answer with Ariel is what exoplanets are made of. We don't know that yet, really. We also want to find out how planets and planetary systems form and how planets and their atmospheres evolve. So presently, we don't really have a lot of information on that, although we have detected quite a few exoplanets already, but we have so little additional information about them that we just cannot answer these questions yet. And with Ariel, we want to do that. So Ariel will be the very first chemical sensors of a large sample of diverse exoplanets. So the very first telescope that will observe exoplanets with a huge statistical sample very systematically to really get systematic information about planetary populations and possibly also a so-called HRD of exoplanets. So if we want to progress in these areas, we fully rely on spectroscopic observations of hundreds of transiting planets that span different planet sizes and equilibrium temperatures and orbiting a variety of stellar types. So I've mentioned at the beginning already, we do face a lot of variety in space out there, what kind of exoplanets are out there to be found. And we really want to get them all, and we have to decide in the next few years which planets, what number of which planets we want to really observe in the end to get the best possible science out of the mission in the end and for exoplanet research. So one of our motivations was that thinking about exoplanet demographics in 2020, not so long ago actually, it was obvious that we do have detections of quite a few exoplanets. It was several thousand at that point already. But we have just a little idea. We know there is an exoplanet. We might have a good idea of how big the exoplanet might be and where around the star it can be found. But that was it for most of the planets. In the best case, we have mass and diameter, so mass and radius measurements, and can determine an average density. But that's already the best case or the best scenario we are facing. So it was really obvious that there is need for more information if we want to find out more about exoplanets and exoplanetary populations. So that's what fostered the decision for Ariel, obviously, as well. The key top-level science questions I mentioned already. We want to find out what exoplanets are made of, how they form and how they evolve, and how the atmospheres actually evolve in the end as well. To also learn about the Earth and solar system history, of course. The observations will be carried out in a way to probe atmospheric chemistry and dynamics. We're going to do transit and eclipse spectroscopy between 1.1 and 7.8 micrometers, and also multiband photometry for the transit observations in 0.5 to 1.1 micrometers. We're going to observe known exoplanets that transit relatively bright stars, a diverse sample from gas giants to super-Earths, also possibly reaching Earth size, but that's to be determined if that's possible. It's not the prime goal of the mission, but if the instrument performs well, it might be feasible. And we are focusing on warm and hot planets to also get information about the interior of the exoplanet. So if the atmosphere is still hot enough, it also gives us information which elements are in the interior of the planet. So that's why we want to go to these temperatures primarily. And then also can get a lot more physics or find out how secondary outgassing affects the planet, atmospheric escape is working, how the atmosphere and the surface of the planets exchange, and how material is accreted onto the planetary surface. So all kinds of physics that we will be able to determine from the spectra of the exoplanetary atmospheres. What we also really want to find out what the position or how the solar system can be related to exoplanetary systems in the end. So we know that the solar system is only one outcome of planetary system formation, but there are many other possible, of course. The solar system, for example, has temperate rocky planets and also cold gas-rich planets. But in exoplanetary systems, we face a lot more diversity. We have very extreme cases, so-called hot Jupiter, so Jupiter-like gas giant planets that are very close into the star, something we do not see in the solar system at all. We do have so-called super-Earths in very high numbers in exoplanetary systems. And these are planets that are also not found in the solar system at all. We do not really know why. Super-Earths are often also called transitional planets. So planets that are slightly bigger than the Earth and usually still have very dense hydrogen helium atmospheres and are likely not livable, but are present in huge numbers in the universe out there. And we want to find out why the solar system, for example, does not have a super-Earth, why there are so numerous in other exoplanetary systems. And there is a lot more to come, I'm very sure about that. So the current times and also the coming years are really very exciting in terms of exoplanetary science. And I'm sure there will be a lot of very, very exciting findings and detections before Ariel is launched. And it will be a very exciting endeavor to continuously update our target sample to really observe the best targets for the mission. Something we will also learn about is migration in stellar planetary systems. So when planets form in disks, they can form more or less in any place where material is there and there is a core upon which an atmosphere can grow. And we do not really know if we have a look at the current exoplanetary system at first glance where the planets might have formed, if they really formed in the place we now see them, or if they have formed somewhere else. But as soon as we can analyze their atmospheres, we see more about their chemistry, we might be able to tell if the planet has formed further out in the disk and then migrated inwards or vice versa. So there is also a lot of very exciting information we can get on this kind of studies where exoplanets have formed in the system and how they have migrated in the end. There was a lot of migration happening in the solar system in the past, very likely as well. So what we can also do, and that's a very central point, is we will be able to go beyond bulk density, which means we do not only have mass and radii, but masses and radii of exoplanets, but we have a lot more information. So if you have a look at the left diagram here, that's a plot mass against radius. Two very different planets, as shown in the picture to the right, they have measurements very close together. So if we just have the diagram here, we wouldn't be able to say a lot about the difference of these two planets, although, as we see here in the picture, they might be very different in the end. So both planets could have rocky interior and hydrogen helium primordial atmospheres, or a water vapor atmosphere and icy interior. So both of these very different planets would give us the same data point in that diagram. And if we have additional chemical information from the Ariel mission, we will be able to distinguish between these two very different scenarios and between further possibilities, of course, as well. So we will be able to really say, now we can only guess, but we will be able to really say if a planet has an ocean-like surface, like this one here. I hope the video works. Yes, it does. Or across the atmosphere, maybe with some organic material as well, a magma ocean atmosphere, or across the atmosphere with different surface composition. So that's something we will be able to find out based on the data from the Ariel mission. In addition, we also can, or we will, and that's a graph to show you how the spectra might look like in the end, and also to show you how different physics of the atmosphere are imprinted in the spectra. So I'm showing you here 3 different curves that are representing different pressure levels. So temperature, pressure gradients are very important measures for a planetary atmosphere. And you see here in green, 10 to the minus 2 bar model of an exoplanet, of an exoplanetary atmosphere, 5 times 10 to the minus 2 bar in yellow, and then a clear atmosphere, spectrum of a clear atmosphere in red. And you see that there is really a big difference, and we will be able to distinguish between these very different planetary atmospheres with the Ariel mission. And to the right, just to show you how sample spectra this is all simulations, of course, but spectra that are typical spectra we're going to get for the molecules I'm showing you to the right. So CO, CO2, water, methane, that will all be there. Titanium oxide for the instrument we are going to have on board of the Ariel mission. And here, just to show you, I thought that might be nice to see as well. Glimpse into the instrument. So this is the Ariel mission in a picture that is currently being built. The project team is attending a meeting with industry today. I'm attending that online as well, by the way, not now, but after this talk again, where aspects of the mission would be defined. Discussions are taking place with industry, how things are designed, if everything is working well. So that's currently ongoing, and we need to be finished very soon, actually, to be able to qualify for launch. So what you see here, or what you saw here, is the path of the light through the instrument and then to the back of the system, reaching the detectors for the, so the path of the light again, falling onto the primary mirror. I hope it's well visible. The video might be quite data intensive. Primary mirror, and then the secondary mirror is reached and then again reflected to the back of the telescope, reaching the detectors, the so-called EARS detectors, and the FGS instrument that is there for spectroscopy, for EARS, and FGS photometry. And also different wave bands, and doing the fine guiding as well. So an instrument that is used both for science and for guiding. We are going to launch on an Ariane 6.2 together with another space mission and another ESA mission Comet Interceptor. So in the last few minutes, let me talk a bit about how important stars are actually for exoplanets, and speculate also a bit, or touch a bit upon on the subject of how important it is, how young stellar objects evolve, living around young suns, is that possible or not, and current research that is going on in this respect, and is also very important for exoplanet science and for the Ariel mission. So when we study stars, it is especially important to consider the magnetic fields, the winds, and atmospheric erosion they cause on young stars around on exoplanetary atmospheres, and also to think about and discuss the implications for habitability. So when we talk about planetary habitability, or about the evolution of a planet to a habitable system, stellar planetary system, there's many different factors. So it's not only liquid water in the habitable zone that is important. It's a very basic main prerequisite, of course, but there are a lot of other factors to be considered when trying to answer the question if a planet is habitable or not. So there is, for example, the initial disk, the disk composition, the star itself, planetary formation and migration. We were touching upon that already. Water delivery, the importance of a moon, plate tectonics, the loss of the primary atmosphere, water to land relations. So I'm quite sure there were quite a bit of talks already on these subjects within the series. There are maybe more to come, but I would like to mention a bit on the role of the star in this talk, and the importance and how important it is to study the central star and the evolution of the star together with the planet in the end as well. So stars, especially when they're young, they can be very violent, and they usually have a very, very strong, very high energy output in the form of flares, coronal mass ejections, high energy radiation in UV, EUV, and X-rays, and winds are launched there as well. And we want to study how radiation and atmosphere interact, how magnetosphere wind interaction affects the planetary atmosphere, and also study the magnetosphere-atmosphere system. So this is to show you how stars really look very different from very young ages to later on. These are only artist conceptions, of course, but a star that is very young very likely very often has a huge amount of spots compared to the sun. You see there's a lot less on later stages. So the sun is quite is a star that has reached the main sequence. It's has an average age, if you want to put it that way. So very likely was more active in the past, but is not that active anymore. So there are young stars that are considerably more active than the sun, which have planets already, and of course they affect the planets in heavy ways as well. And for the sun, actually, so for the solar Earth system, for the solar planetary system, we do not know how active the sun really was in the past. If it was a very active star or not so active one, so there can be anything happening in the end. It all depends a lot on the rotation period of a star. And for the sun, we do not know the history, so we do not know how the sun and the Earth evolved to a habitable system for the Earth. But of course, that would be very interesting to know. And by studying other stellar systems, we might learn a bit more about that. But you very likely can imagine that when a star is very active in the past, it might be very difficult for a planet or not. So, but it's certainly posing very different boundary conditions to a planetary system. So this is just to show you how, for example, a star and the planetary magnetosphere could interact. So for the Earth, we do have a magnetic field that is shielding us, but on the other hand, we do not really know if maybe the magnetic field is also launching or is also causing atmospheric loss. So actually, we do know that it's causing loss, but we do not know if the magnetosphere has more of a shielding effect in that respect or not. So that's also still an open question in exoplanet science. I'm showing you here just to illustrate a bit how these wind, how the magnetic output of a star, how the activity output of a star looks like. Again, using the example of the sun, these are solar orbiter observations from the last year. So you see quite nicely how energetic, how flares are erupting, how coronal mass ejections are happening, and how violent it can be around the star, whereby the sun, as I mentioned already, is a very moderately active star at this point. What is caused by this energy output, actually, I guess you're all aware of that, is the so-called northern lights. So the more active the sun is or a star is, the bigger the effect on the atmosphere is. And we see that very nicely with the interaction of the Earth's magnetosphere by having northern lights in the northern hemisphere. Maybe some of you have seen that beautiful spectacle already. That's only one effect, and many others are there, of course, as well. So as I mentioned, different activity output might be very important for, or is actually for sure very important for planetary evolution, but we do not really know yet which levels are really ideal, how it worked for the solar Earth system, because we do not really know how active the sun was in the past. So it could either be the case that a star needs to be very active to be able to blow the very first atmosphere away, the hydrogen-helium envelope, many planets are very likely having in the beginning, so that because only when this primordial envelope is blown away, a secondary atmosphere can evolve that can be enriched with oxygen and other elements that are important for life. On the other hand, so we might need a good level of activity in the past, but on the other hand, if this activity is too high, the secondary atmosphere would also be blown away and could have a very detrimental effect. So there might really be a very delicate balance necessary to have, for example, a star that is active enough, but not too active. And of course, it also depends a lot on the planetary mass. The more massive a planet is, the thicker, the denser the atmosphere it accumulates. And so there's a lot of interplay between these different factors. And actually, hopefully, a lot of different scenarios might be possible to in the end lead to a habitable planet. So I would like to show you in this graph shortly how different or how important the energy output in the stellar history is for a planet. So if you have, it's again a plot age against X-ray luminosity and the UV luminosity for a star that is rotating very rapidly in its history, and a slowly rotating star depicted in green, an intermediate rotator in red, and intermediate rotator in green. And you see that all these different rotation levels, rotation is very closely linked to activity. These activity levels, they lead to very different energy output. So you have, for the very rapidly rotating star, you have 20 times the extreme ultraviolet radiation output and 40 times the X-ray output. And that is really posing a very different scenario on any planet around these different types of stars. And what makes it also so important to study and to know how active a star is and how it evolves is the fact that exactly in that time span, where these crucial differences happening, the planetary atmosphere is forming, the crust and plate tectonics are settling in, and the oceans are there and evolving as well. So it's really crucial to study these effects and to know what the common history of a star and a planet is. And just to finalize, I would also like to mention, as this is very often on the plates in publications and in discussion on exoplanets and exoplanet missions, is the so-called M dwarfs. These are quite small stars, quite cool stars that are very popular to be studied because they are so numerous in the universe as well. And it's a lot easier around them to detect exoplanets because the habitable zone is a lot closer in than around solar-like stars, because they are just cooler, and the zone where liquid water can exist is a lot closer to the central star, and we can observe the transit more often. A very famous system you might have heard of already is TRAPPIST-1. It's heavily studied currently by JWST, so we're really excited what data we will get from that system. And this is just to show you the comparison. We have the solar system, Mercury, Venus, Earth, and Mars. And for TRAPPIST-1, there are 7 planets that are all of them packed very close to the to the star. So if you zoom out that area, the whole TRAPPIST system would just fit in very well within the Mercury radius. And this really shows very nicely how close in the planets are. And it's, of course, very tempting to think that planets around M dwarfs might be very well livable. But we also need to think about the fact that around M dwarfs, the habitable zones are actually shrinking. So due to the fact that luminosity declines in very different ways, you don't need to have a very careful look at that graph, but just keep in mind that for M dwarfs, we have very large luminosity declines throughout the evolution, different to solar-like stars, K stars, and sun-like stars. So the habitable zone is actually shrinking, and it's hard to imagine how a planet in the coevolution with the star can get conducive for life. Maybe it's possible, but it's something you need to keep in mind. And also, M dwarfs are staying active for quite a long time. So they are not necessarily more active than solar type stars, but they spin down very slowly. Often, not all of them, but many of them do. So they stay at very high activity levels for a long time. So the planetary atmospheres around them, planets with the atmospheres around them, they face very different conditions. So that's something to keep in mind as well when thinking about M-dwarfs. So going back to Ariel, we are going to do it all, more or less, if I may say. So we are going to observe M-dwarfs, K stars, G stars, and also F stars, F to A stars. And we want to observe in great detail the 1,000 at the time most interesting targets to really get the diverse sample, the characteristics of a big sample, and get a lot more information on how, on a systematical basis, how exoplanetary atmospheres form and evolve. And let me finalize with a statement that when I think about it, it still creates a bit of gooseskin, I have to admit, but it's actually true. We are the first generation to know that the ancient hypothesis about planets around other stars is true. So it's really amazing to think about that. There was speculation in the past, of course, but we know it's true, and it's not that long ago that the first detection happened. And we are also the first generation that is capable of studying these other worlds. So we are really living in exciting times, and I'm very thankful about that, to be honest. And Ariel is one of the key missions to study these other worlds. So thanks a lot for your attention. And if you want to find out more about the mission, I've included a few web links here, and I'm happy to take your questions.